We're ready for Chapter 12 and tropical weather. Our driving question here is what conditions are required for the development of tropical cyclones? Hurricanes are the main tropical cyclones that we talk about. And a hurricane is an intense cyclone that originates over tropical ocean waters, usually in the late summer or early fall, and it has maximum sustained wind speeds of at least 74 miles per hour. Now, if we compare this with an extratropical or mid-latitude cyclone that we talked about previously, there's no associated front or frontal weather for a hurricane like there is with the mid-latitude cyclone. It's simply due to a uniform surface of warm, humid water and lots of intense solar radiation heating. The sea level pressure and steep horizontal air pressure gradient are typically much greater for a hurricane than they are for a mid-latitude cyclone. A hurricane is a much smaller system. It does not affect as big a region as a mid-latitude cyclone. And a mature hurricane is what we call a warm core low, whose circulation weakens with altitude, whereas with the mid-latitude cyclone, it's a cold core low, whose circulation strengthens with altitude. The etymology of the word hurricane comes from a Taino language from a tribe in Central America, the word huracan, which means god of evil. And in the Pacific Ocean, we call them typhoons. That word comes from the Chinese, meaning big wind. And the word cyclone, which we use for a low pressure system, is from the Greek word kyklos, which means circle. The characteristics of a hurricane include the eye of the storm, which is the center of the hurricane. It's where there's no clouds and the air is subsiding, there's light winds, so if you're on the surface and the eye of the storm is passing over you, it seems like just a fine weather day. The diameter of the eye can be anywhere from 6 to 40 miles, and the tighter the eye, the stronger the hurricane. Another characteristic of a hurricane is the eye wall. These are the clouds that border the eye of a mature hurricane. They are a ring of cumulonimbus clouds, so there's very heavy rains, very strong winds, and this is the most dangerous and destructive part of the hurricane. So if you're standing in the path of the storm and you look at the right side of the eye wall, that's going to be the area of most destruction, the strongest winds and strongest thunderstorms in the northern hemisphere. Another characteristic are the cloud bands that spiral inward towards the eye wall. These produce heavy convective showers and are hurricane force winds. And then up at higher altitudes, we'll see cirrus or cirrostratus clouds that are spiraling outward from the eye of the storm. Let's take a look at a schematic. Here you see the eye of the storm in the center, and it's surrounded by the eye wall, which is made up of big cumulonimbus clouds. And so we have basically a big system, a low pressure system. So that means the rotation is happening counterclockwise and inward. And you can see here some of the characteristics. We have the spiral rain bands that spiral out from the storm, but the general circulation again is going to be counterclockwise. And then the higher altitude winds that are kind of driving the direction of this thing. Here's a satellite image of a hurricane. This is Hurricane Elena from 1985. You can see the very well-defined storm, the spiraling clouds. You see the eye of the storm here, the eye wall, the very thick thunderstorm clouds on either side of the wall, the counterclockwise motion, and you see these cirrus and cirrostratus clouds kind of on the outer edges of the hurricane, with the clouds thickening into big cumulonimbus clouds as we get closer to the eye. Here's a cross-section of a hurricane. So we have the eye. This is going to be the lowest pressure here. This is the center of the storm. On the sides of the eye, we have the eye wall, where we have our most massive convective uplifting happening. And we have this complex circulation pattern happening with most of the uplift at the eye wall, and then outflow, and then to complete this circulation, subsidence on the outer edge of the hurricane, and then convergence coming together because we have this low pressure system here. So you can see the altitude, how high up into the atmosphere this goes. It tops out at the troposphere, and the extent, in this case it's at 500 kilometers. Here's a surface map of a hurricane. So we see, this is from 1998, late September 1998. This was Hurricane George. And what you see here is a very intense low pressure system. So we have our tightly defined isobars that are leading into the low pressure here. And if you can see any of the pressure values here, you see that they're getting lower and lower and lower into the center of the storm, and the wind barbs indicating the counterclockwise and inward rotation. The conditions for hurricane formation include high sea surface temperatures. So by high temperatures, we're talking about 80 degrees Fahrenheit through a depth of about 150 feet, so a pretty deep chunk of warm ocean water. And this is going to sustain circulation because that warm, moist air is going to be releasing latent heat as the liquid water evaporates into water vapor. So because of this, most Atlantic hurricanes develop in the late summer and early autumn when the sea has heated up. The official hurricane season is from June 1st to November 30th, and the peak threat to the U.S. coastline is from mid-August to late October. In the graph you see here, we have a relationship between hurricane intensity and sea surface temperatures. The solid line is sea surface temperatures, and the dotted line is something called the Power Dissipation Index. It's a measure of hurricane intensity. The times when we have warmer sea surface temperatures are the same times that we have more intense hurricanes. Another condition for hurricane formation is adequate Coriolis effect, and it's the apparent rightward deflection of objects in motion in the northern hemisphere. And you might recall from the Coriolis effect when we talked about it that the Coriolis effect is weakest at the equator and strongest as we move towards the poles. My apologies for this blurry picture. It was the best one I could find, and what it's showing here is winds and their apparent rightward deflection, and you see that they're deflecting the most up here by the pole and the least down here by the equator. So we have to have enough Coriolis effect in order to give the cyclone the spin that it needs in order to develop. For this reason, we don't really see hurricanes around the equator. About 5 degrees north and south along the equator, we don't see hurricane formation simply because the Coriolis effect is not strong enough. Other conditions for hurricane formation include weak vertical wind shear. If we have strong vertical wind shear, it doesn't allow for the cumulonimbus clouds to grow. It kind of topples them over before they get big enough. And the last factor for formation of hurricanes is relatively humid air in the mid-troposphere. So when we look at all these together, we can identify source areas where hurricanes are likely to form. So we can knock out the area around the equator because the Coriolis effect is not strong enough. But around the equator, we have the conditions of warm sea surface temperatures. We have lots of moist tropical air, so lots of humidity. We have all the other factors in play. So these areas in pink are the main source areas. And you see the different names that these are called in different parts of the world. So here for us, where most of our hurricane weather happens, we call these hurricanes. But if you look at the Pacific closer to Asia, they call them typhoons. In the southern hemisphere, they call them cyclones. Okay, that concludes the first part of the lecture for Chapter 12.